Okay. All right. Hello, friends. So I'm recording this lecture on time this time. And that's because I'm very excited to give this lecture, which is about the Big Bang and the theory of relativity as sort of discovered by Einstein um, over 100 years ago, actually. Even though for many of us, this is still uh, unknown information. And actually, for me as a scientist, as a climate scientist, before getting a crash course in relativity by Catherine Schaefer, who is our physics teacher at the school, um, I had actually never really studied the theory of relativity or thought about it all too much from a sort of scientific perspective. Um, so bear with me. I've given this lecture a couple times now, so I think I know what I'm talking about, but kind of gonna walk through this. We're gonna walk through this together. So today, so it's broken up into two parts. We have two classes left. So today we're gonna talk about gravity and equations and the idea of a physical theory. We're gonna talk about Einstein, the person, and the history, an introduction to relativity, and then we're gonna touch on arrogance in a good way. Then next week, we're going to talk more about the sort of physical theory of relativity and its relationship with ideology. And then we're going to revisit arrogance, scientific arrogance, but in a bad way. And then we're going to talk about the universe and the Big Bang Theory in more detail, and that'll be sort of the fun part of all this. Some bonus themes are that math is weird. So bear with me with that. I'll try not to get into too much math detail. And also that aesthetics, right? We're all familiar with aesthetics, definitely influences physical theories. And you'll see that with the theory of relativity. So the first thing I want to do is this group exercise. So obviously I'm recording this lecture, so I want you to watch this, and then I want you to just do this kind of on your own, and then we'll talk about this tomorrow. So first I want you to sort of collectively remember a core rule from geometry, like about triangles or distance between points or parallel lines. And then I want you to think about, where did this rule come from? Did humans make it up? Is it a fact of nature? Is it something we just know? Is it a truth? So where did it come from? That's question number 2. Question number 3, if this is a fact or a truth about nature, and it works and on Earth, do you think that it works everywhere in the universe? So that's kind of a yes or no, maybe why. And then part 4 is, okay, now break your rule. You just came up with this rule, this truth that you've always known. Now break it. Think of a shape or a scenario that clearly violates this rule. And we'll talk about some of these tomorrow if some of you are particularly proud of your rule. This is to get our brains thinking about objectivity again, right? So we're revisiting objectivity in science and also math, and why math is so weird that there can be rules that can be broken and still be true. And so before we get to kind of an important sort of math rule, you can see where I'm going here, that can be broken, let's talk really quickly about what we mean by theory. What does a theory look like? Can it be proven? Where do new theories come from? If there are multiple theories talking about kind of the same thing, how do we decide between those theories? And if a theory is wrong, do we just throw it out completely? Or is there some utility for it in science in another way, maybe, or in math? So let's talk about a theory that maybe all of us know or have learned at some point in our lifetime, which is the theory that if you have two masses, right, the theory of gravity, essentially, two masses will be attracted to each other per force 1 and force 2. And according to this theory, those forces, force 1 and force 2, must be equal, and they must be equal to gravity, a constant, right, times the mass of the first object, the mass of the second object, divided by the distance between them squared. This is a real life physical theory that relates our existence on Earth to the Earth, right? It's sort of quote unquote why we're stuck to and attached to the Earth. This is Newton's law of gravity. Sorry, let me just move myself. So some questions that I want you to think about as we go through this are, what is the model of gravity here? How does this theory function? And what would it mean for it to be right or wrong? Okay, so Newton, who lived hundreds of years ago, who laid out several physical laws, Newton's laws, relating to gravity and mass and force and those sorts of things on Earth, right? He was on Earth. He said that gravity, G, is a constant. It's a constant value that we know, 9.81, right? We all know that. Maybe we don't all know that, but we all learned, maybe in high school or college, if you've encountered this in another class, that gravity is 9.81. So this theory assumes that gravity is a function. You have known masses and a known distance between those masses, and you can determine exactly how attracted, what the force between those two objects is going to be. Supposedly, according to this rule, this is why we are not falling off the Earth. We're attracted to the Earth through a force known as gravity. Okay? And here are some crazy equations, some mathematical equations where we can use Newtonian gravity to kind of expound on this theory to derive a relationship between the orbital period of a planet, its distance from a star, and the mass of the star. So if we're thinking about Earth, we can actually derive the relationship between how long it takes Earth to orbit the sun related to the distance that we are from the sun and the mass of that sun. So we can use and apply Newton's law of gravity, and it really does work. This is a real thing that works, supposedly. So this is a theory, and this is a theory that pretty much every Physics 101 class will teach, and it's not really that unusual or controversial of a theory. This is Newton's law of gravity. We can use it to determine the orbits of the planets, the masses of stars, the masses of planets, etc. Right? All using Newton's law of gravity with a gravity constant, G. And we did just that. We did it for the whole solar system. We're able to derive the orbits of the planets, the masses of the planets, how far away from the sun they are, and we know a lot about our universe using this law, Newton's law of gravity. Okay, again, reminding you about the law. When we use this law, this model, right, it gives predictions for orbits that match exactly what we can measure using a satellite instrument. So the law essentially works. Newton's law from 400 years ago works just fine. But something I want you to consider here is, what doesn't this law mean? What are some limitations of this law? I want you to not think necessarily, is this law or is gravity real? Is this law correct or complete? Or that future measurements with greater precision will continue to perfectly agree. They may or they may not. They probably will. But what I want to kind of highlight is that this law isn't right or wrong per se, but according to Einstein's theory of relativity, this law does not apply. You could say it's wrong, but it does in fact work. It does in fact give us information about gravity, about the orbits, about the sun, about the mass of planets, all of that stuff. So it's not necessarily wrong, but it is wrong, actually. it's not it's not the truth per relativity, but I'm hesitant to say that it's wrong, because that means that it's useless, and it's not useless actually. And I'll explain why in a moment. So let's walk through briefly the timeline, the obligatory history, let's say, and there's a little is it history, because as we'll talk about in a moment, history and time are not linear in the way we think about them, but of space, time, light, and gravity. Okay, so in 1632, Galileo thought about movement, about ships passing in the night, right? About ships moving. And he kind of came to this conclusion, among many other conclusions that he came to at the time, which were revelatory, that there was no absolute meaning of stillness, and there was no absolute definition of motion. We think we know when something is moving, and we think we know when something is not moving, but we actually don't really. With our own perception, with our own eyes and our own ears, we don't really perceive movement and stillness. So this goes back to our lecture from the beginning of the semester, talking about observations and how our eyes and our own senses sometimes deceive us. That what is objective is sometimes not always determinable by our own perceptions. In 1687, Newton laid down the laws of motion and universal gravitation, and his formulation of these laws depended on the absolute meaning of time, and usually assumes absolute space, like space between things, is real, right? But he did encounter some problems when he talked about this. So for him, time was a fixed value. He was doing these measurements on Earth, and time itself was a fixed value. Space was also fairly fixed value for Newton, meaning the distance between me and my laptop is something that I can measure, and it's real, and it exists everywhere, right? The length of time that it's taken me so far to give this lecture is real, it's measurable, and it's applicable to everywhere in the universe. That's what Newton said. Fast forward about 200 years, in 1862, Maxwell, physicist, worked out the mathematical laws of electricity and magnetism, which seemed to, at the time, imply a constant speed of light, regardless of reference frame. And this is really important because this is a very different outcome, conclusion, than Newton and Galileo. In Newton and Galileo, they're assuming that all time and all space are constant and absolute, right? But Maxwell is saying actually the only thing that's constant is the speed of light. And I'll get to this in a moment. So a couple years later, Michelson and Morley did an experiment which showed that light, the speed of light, since it has a speed, it means it's traveling, right? It did not require a medium through which to travel. It did not require an ether, so to speak. This is important because light can travel, the speed of light, and light exists in a vacuum space. There can be nothing there, and light can travel through it. So now the theories of Newton, the laws of Newton, are starting to break down. And along comes Einstein, who between 1905 and 1915 derived the theories of special and then general relativity, where he removed absolute space and absolute time and created a new theory of gravity, which can actually explain the whole universe in a way that Newton's theories of gravity and time and space cannot. So Newton did end up being wrong, but not fatally so. His equations are still very useful. They're just not correct, if that makes sense. And we'll get to that in a second. So we're about to talk in very, very extensive detail about these terms, about relativity, Galilean relativity, special relativity, and general relativity. So let's define in our heads, I'll give you a moment here, define in our heads what relativity means. And it does mean kind of what you think it does, relative. Would you say that relativity relates to a subjective experience? Typically, when we say something is relative to something else, that is kind of subjective, right? In this case, though, the theories of relativity are going to be objective. And do these theories relate to anything that we would normally experience in our everyday lives, do you think? And these are important questions that we're going to hopefully answer. All right, so in your life, you have relativities, right? There are, I would loosely define relativity in our everyday life as variations in subjective experience and judgment based on different social, cultural, personal frames of reference. So it's hot out to me relative to my own experience. It might not be hot to someone who's coming here from South Florida. This might feel cold, but to me, 70 degrees today feels warm, right? That's a relative experience. That's relativity in my everyday life. Relativity in physics is a very different thing. Relativity in physics is an objective measurement of time, space, and motion that deal with space-time frames of reference. There are three types of relativity. There's Galilean relativity, which we won't really talk too much about, and then there is special and general relativity, which are the theories outlined by Einstein. So Galilean relativity relates really well to our own personal sort of experience with relativity. They're features that are describing everyday experience. They have relatively little, to do with Einstein's theories, kind of, right? So Galilean relativity is saying that I'm sitting here and my partner just walked by me, so relative to my position, he's moving and I'm not. That's not a correct physical framework because in reality we're all moving, but relative to me, my partner just moved by me. That's Galilean relativity. That's very similar to relativity in my own personal existence, but very different than special and general relativity. They're very different ideas. Special and general relativity together are Einstein's theory of relativity, which is still the reigning theory of physics, of space, of time, and of gravity. This is how we can describe all of the universe, all of the physical world, everything, with special and general relativity. So Catherine would like me to plug her course, which is Articulating Time and Space, which is going to deal with the mixture of these two concepts and be a really, really, really much more, a deeper, more in-depth dive into relativity in physics. Okay, so I also mentioned while we are going to be talking about the science of relativity, we're also going to be talking about Einstein as a scientific figure, because this class is not just about the science, but it's also about viewing scientific accomplishments and scientific thought through a framework which allows us to, hypercritically analyze the truth, right, and think about the truth and objectivity. And so with that, we need to understand Einstein himself, because Einstein himself is like a very pivotal figure in not just relativity and physics, but also in science in general. And in the context of this course, he's up there with other people that we've talked about as being sort of instrumental in our understanding of what is actually true in science. So in 1902, Einstein, who was very young at the time, took a job in a Swiss patent office after an undergraduate degree in physics. During that time, he started thinking about physics. He wasn't actually in grad school. He published 2 papers in 1905 that he wrote and researched while he was working at the patent office. they would totally revolutionize physics. One of them was on quantum physics and the other was on special relativity. At this time, he was considered an outsider. He was not in grad school. He was not in the ivory towers of academia. He wouldn't have been considered a very serious scientist. And yet, his publication on special relativity totally transformed science and is considered by many to be one of the crowning achievements in scientific knowledge production over the last however many years. So in 1907, he's like, okay, I did a lot of stuff. I should start working on a general relativity theory to explain everything in the universe. In 1909, he got the first of several professorships of faculty positions that let him be a physicist actually full-time. And in 1916, he finally, 8 years later, completed his theory of relativity, which was sort of incredible and changed the course of physics forever. And then in 1917, he took an amazingly arrogant but important leap, applying his theory of general relativity to the entire universe, launching the field of, I don't know actually what is written under there. Let me move things around here. Cosmology, that's right. I knew the word, but couldn't remember it. Okay. So the theory of cosmology launched 1917 by Einstein, drawing on his themes from the theory of general relativity. So I wanted to take this opportunity to talk about geniuses and outsiders and crackpots and this whole idea in science, but I'm going to save this for our Zoom meeting tomorrow, because I think this is an important discussion to have together, actually. Okay, so pre-Einstein, right? Galilean relativity. Let's talk about what relativity actually is and trace the steps of how Einstein got to this very arrogant step, good arrogant, where he applied his theory of general relativity to the whole entire universe. So Galileo was one of the first people to think about nature and think about movement and think about things as not actually being at rest or in motion, mainly because there was no real test that you can perform that will tell you if you're really moving or at rest. How do you do that, right? So while we think we can perceive things moving around us and think we can perceive things resting or not moving or still, we actually cannot. And there is actually no such thing as rest or movement or motion, in the sense that we have, up until this point, unless you've taken a course on relativity, up until this point, it's possible that you've actually never thought about this. But it's true. You cannot perceive motion and rest and stillness. These are all pre-Einstein ideas, but they're very influential for his theory of relativity, right? And so what Galileo said was that motion is an entirely subjective, relative experience where it was perceived due to your perspective, okay? So we have two boats here, all right? The person on boat one on the left, let's say, is at the top of the boat, and he drops a pair of binoculars. Sorry, there's actually only one boat in this drawing. Or there's two boats drawn, but there's only one. It's the motion of one boat. So the person on the boat is at the top. They drop their binoculars. To them, the binoculars drop straight down, and they land on the boat. But if the boat is moving, right, in a direction, I guess it would be moving this way. Yeah, it would be moving this way. Then actually, from someone standing on the shoreline, the binoculars actually trace a path like this, right? A curved path. Whereas if you're on the boat, they follow a straight line down. Okay, so this is Galilean relativity. Motion is not a real quantifiable thing. It's based on perception. This will be important to Einstein as he takes kind of the next step to translate this experience to actual all of physics and all of motion. So in everyday experience, for the most part, we act as humans, as individuals on the planet, like we have an absolute frame of reference, which is the Earth. Okay? Therefore, we intuitively respond that a person in a train, for example, moving by us is really moving, and a person that's on the platform asleep is actually at rest, because the frame of reference is the Earth itself. So if I am standing at the train stop, right, and I'm sitting on the bench or I'm on the platform asleep, and a train goes by me, I perceive the train as moving in motion, and I perceive myself as at rest and sitting. Einstein and classical physics undoes all of this frame of reference. And what it says in a nutshell, and I'll try to walk through some of this, is that uniform straight motion is actually equivalent to rest. They are indiscernible by any experience, experiment, or measurement. Meaning if I'm asleep on the platform, I am actually moving in a uniform straight motion, as much as the train is also moving in a uniform straight motion. Equivalently, we are both at rest. Or not, because at rest doesn't actually mean anything. So actually, we're all just moving. I hope that makes sense. This is really hard to give, actually, I'm realizing now, to my computer screen, because normally you all would be looking at me like this. I can't actually do the eyebrow thing. Or like one eyebrow's up. Whatever. But so I hope that I'm able to explain some of this in the Zoom tomorrow. So not only does place have no absolute meaning, moving versus still have no absolute meaning, and they're non-concepts. They're not even real. And we're not even into relativity theory yet. It's just that the idea of motion and stillness they're actually just, throw them out. They're wrong. Nobody is moving or not moving or still or not still. Everything is, let's call it in motion right now. But eventually everything is in a time-space continuum where movement is considered to be something that's along the lines, the contours of time and space. If you're watching this and it's the evening and you enjoy partaking in cannabis, I highly recommend being high when you think about time and space, because I think it actually makes more sense. For real. And there's like a cool YouTube series called Space Time, which is great to watch. And it's like short little videos that will explain all of these concepts in probably better detail than me. All right, so here is Einstein's theory of special relativity. So when we talk about speed of motion, we're always talking about speeds relative to the observer. And I am going to do a demonstration of this tomorrow in the Zoom. The only thing, however, that does have an absolute speed in the world is the speed of light. Light itself is always moving at the same speed, traveling at the same speed, which is the speed of light. It's the same if I'm moving 1 million miles an hour or 0 miles an hour. light is moving the same speed in both of those instances, also relative to my own speed. So that's fucking insane and really difficult concept to wrap your head around, but light is always moving at the same speed. The only time that light would perceived to be still to your relative position is if you yourself were also moving at the speed of light. So to make this work mathematically, space and time actually have to be described as a four-dimensional space-time. So normally we think of time as something that just moves from the last second to the next second to the next second to the next second, and we live in this space which is three-dimensional, which has an x-axis, a y-axis, and a z-axis. But actually, we live and exist in a space that has an x-axis, a y-axis, a z-axis, and a t-axis, which is time. Time is a dimension of our existence. So in order for this mathematical concept, the speed of light, to actually work mathematically, space and time must be able to stretch and contract in response to relative motion. So if I, even just saying this out loud to an empty screen feels like I can feel your confusion, and I love it. I hate it, but I love it, because it's such a crazy concept. And I'm going to explain this in more detail tomorrow. But basically, let's use the example of me sitting on a train platform and you on the train itself. Now, let's say that I'm on the platform, so I'm on the earth, so I am also in motion. I'm traveling through space-time, right? But you're on the train and you're going half the speed of light. You're going really fast. I mean, if you were going half the speed of light, that would be amazing, and you would be the only person ever to have done that. But let's just say that you're moving past me at the speed of light. For you, not only are you just going to be moving faster, okay, but you're also going to be moving through space-time differently. Time in your situation, going half the speed of light on that train, is going to be like at 1 second for you is going to be different than 1 second for me. Kind of. Okay? So time and space will either dilate or contract. And I've got an explainer for this. So I will explain some of this more tomorrow. I just want to introduce it right now. So space and time are not an absolute value. They're linked together, and their fundamental properties depend on perspective. In this case, perspective is not a relative term. Perspective is like, what is my body doing versus what is your body doing, or what is my object doing versus your object. It's a really lovely idea. It's very elegant physically, but the reason actually it's stuck around is because it's true. It works not just here on Earth, not just in our solar system like Newton's law, but it works everywhere with everything going any speed. It's a beautiful, beautiful theory. So that's the theory of special relativity. And in order to keep this lecture kind of short and concise, I'm not going to get into the real detail examples. I'm going to save that for the Zoom tomorrow, and then y'all are going to be free to ask me questions if you have them. So we'll spend like 30 minutes going through some examples of what special relativity and general relativity are, how this makes sense in a bigger picture, and then you'll have 30 minutes or so to ask me some questions. So Einstein took this theory of special relativity and then applied it to the whole universe. So thinking not just about motion, but also about matter, like mass, like a thing. So really, actually mass or matter is only one type of thing. What we're really referring to is any form of energy can change the space-time framework. So space-time is something that can explain everything that exists everywhere, ever. And the shape of that space-time responds to motion, okay? And it also responds to matter, or to energy, to mass, which makes it change shape. And when that mass or that matter is so big, like let's say the Earth, it can actually change the shape of space-time so much that it becomes very curvy. And curvy space-time is gravity. So gravity is not a force. Gravity is not an attraction keeping us bound to the Earth. It's actually just a very, very curved space-time. So you can think of it like, I wish I had, actually I think I still have. I will draw you what this means and post it in the Slack. But curvy spacetime essentially means that we are not really being attracted to the Earth. You can think of it like we're falling onto the Earth, because spacetime is curved in such a way that the only place we could be is right here on the Earth, because the Earth is so big compared to us, right? So we're attached to it because space-time curved, and think of it like as we're going down a water slide into the Earth. We're curved along space-time, and we're stuck here to the Earth, not because it has a force of gravity, but because space-time curved and brought us together. And the reason space-time curved is because the Earth is fucking big. So, Einstein actually said, Newton, your theory of gravity is shit. And actually, gravity is just curved space-time. And so this is now an entirely new theory of gravity, a new equation describing how it works, and a new idea of what gravity is like, period. And here's how this is typically represented. The grid is space-time. The sun and the Earth are big, massive objects in the fabric of space-time, and so they curve it so much that you can actually see, right? You can kind of visualize this curved space-time line into the Earth is kind of like us, right? We're curved, falling into the Earth. Same with the sun. The sun is curving space-time so much that the Earth is kind of falling into the sun. Hence, we are actually orbiting the sun. We can't really escape that because space-time has been curved so much that the Earth is stuck there. So it's not gravity that's attracting us to the sun. It's the curved shape of space-time. So it's also important to remember that on small scales, like the solar system, which we're going to consider small, space-time can be curved like this, and we can actually see it. We can see the curvature, and we can determine, gravity based on that. But if we look at the whole universe is still appears flat to us mathematically. Okay, so the universe itself is flat, but space-time can be curved among the various components, energy components of the universe. Damn, I'm confusing you so much. So here is the new and improved and updated version of gravity, according to space-time. And I'm not going to go through this equation. So here's the old theory of gravity. Oops. We can update it to our new knowledge of space-time, and I will note that in small gravity situations like our solar system or Mercury or Earth, right, versus like the Milky Way or like parts of the universe, this equation has almost identical predictions to Newton's law of gravity. So for example, for our solar system, it works because it's small enough. Okay, the precision goes down, but it works enough. Interestingly, though, this new theory of gravity has some very interesting new predictions and applications. And it says, if we return to our first activity, like on slide 1, geometry really actually is not the same everywhere in the universe. Okay, a triangle is not just a triangle. Parallel lines are not just parallel lines. Although the ways in which it is not the same are still things that we can use math to solve. So even if geometry is not real everywhere, or the same everywhere, that doesn't mean that math is irrelevant or useless. We can actually still use math to solve lots of things. So let's return to these pictures, because let's talk about the aesthetics of relativity, okay? So the aesthetics of relativity, it's really hard to represent these processes, to represent curved spacetime, curvy spacetime. So for example, the sun, which has a relatively low mass, curves spacetime a little bit, relatively. A neutron star, which has a much higher mass, curves spacetime a lot, and a black hole, which has an extremely high mass, curves spacetime so much, right, that this is typically how it's represented, that the curvature of spacetime is so high that you fall into a black hole and can never get out, right? You fall into the sun, you can get out. Maybe like you can't, but something could. A neutron star, spacetime is curved a lot, you could still get out. Black hole, spacetime is curved a ton, and you can't get out. Black holes are actually an extreme example of how spacetime can curve. And I'm going to present this slide, but then I would love to be able to talk about black holes with Catherine and you all. So I really want her to be able to join us. So I'm not going to spend too much time talking on this. I'm going to leave this slide up here for you to look at. Kind of the aesthetics of it, how the curvature of space-time works with a black hole, what things like event horizons and singularity mean. But I'm going to spend more time next week talking about black holes and hopefully get Catherine to come and chat with me a bit about them when possible. Usually she would come into the class, but it's hard to kind of work out the timing here. In the interim, you can watch the movie Interstellar, which actually does a really good job talking about black holes, believe it or not. So we then can so Einstein goes from special relativity to general relativity, and then takes general relativity and applies it to the entire universe per this equation, which one of Catherine's students got tattooed on their arm. Here's the equation. And so Einstein basically said, and we're going to save this for next week when we talk about the Big Bang, but we can treat the entire universe as a physical system that we can apply a single equation to represent. And what happens when we do that is we get the theory of cosmology, the theory of the Big Bang, yada, yada, yada. One of the biggest controversies of the last 100 years in physics. All right, so there are a few extra slides here, which I will present because we're not allowed to ask questions. So I thought that these would be good slides to show. So typically, space-time is represented in an aesthetic way by these gravity wells, right? They're not perfect, and they actually don't really represent the physics very well, but they're ways that people are thinking about how to represent this very complicated concept of space-time in an aesthetic way. This equation, this big general relativity of the whole universe equation, is basically just showing a bunch of numbers. The Friedmann equation, right? You have gravitational constant, which is the strength of gravity, not actually gravity itself, but the strength of gravity, right? Because Einstein kind of redid the whole paradigm. C is the speed of light, and H, which is the really important variable, is the rate of expansion of the universe. So I talked about how Einstein was arrogant. He was arrogant because he took his theory of general relativity as an outsider, as someone who wasn't in science. Oh my God, coming in here arrogantly and saying, I have solved it. And it was a good thing he did that. It was a good thing he took that leap of faith, because he did, in fact, solve it. He did lay out the theory of general relativity. And then he said, let's apply it to the whole universe. And people were like, damn, he's right. So it's very arrogant to go from, an outsider with no graduate degree in physics to describing the entire physics of the entire universe. That was a huge, arrogant leap, and it's a good thing he took that leap, because we may not have had this theory without it. Okay, so sometimes arrogance in science is good. But then Einstein got really arrogant, and he said H, the expansion of the universe, was 0. Einstein said the universe was not expanding, that it should be unchanging, it should be perfectly described by these equations. It turns out, actually, and he said this very arrogantly and was challenged, actually, and it turned out that he, in this case, ended up being wrong. And so this is a little teaser for next week, that sometimes arrogance in science is a good thing. Sometimes arrogance in science is a bad thing. And so I'm going to leave it there. And I'm sure I've confused the fucking hell out of you. And so I hope that we spend a lot of time tomorrow going through some of the details of this and trying to iron out some of the confusion with the idea of relativity. All right, cool. How do I stop?